Hello, welcome. Did you miss me? Yes, of course you miss me because you got to learn the feel of this chapter, dual nature. Feel of this chapter, dual nature. So we'll continue this chapter, dual nature, by our new things. You know, myself, Tofik Nek, and welcome you to added, the place where we add some knowledge to your brain. So let's get started. In the previous class, we studied some important topics. We'll continue that thing by studying this basic and very important topic. In this section, we are going to cover many interesting topics like photoelectric effect. Wait one second. Photoelectric effect. Okay, photoelectric effect. Energy, momentum, and photon. Einstein equation, we'll see Einstein equation, which is very important, important. Einstein equation very important, and threshold frequency, threshold wavelength, and previous year question. Just so simple. Okay, let's get started. So before that, why everything why we need to study. Now see, in ray optics, basically light has two behaviors. You can say light has two behavior. We know light, basically light. It is known. It is fixed. Basically light. Wave nature. This we studied in our ray optics and wave optics, and we proved this phenomena by many kinds of you can say methods. In that important methods, we proved this wave nature phenomena by interference and diffraction and polarization. By these three methods, we proved that light is a wave nature. Okay, now not only this, at the same time, light behaves like a particle nature. How? See, light travels in the form of photon. Photon is like electron. Photon is energy. Photon is a particle. So we can say light travels in the form of particle. We'll discuss it very deeply in next slide. Now just remember, light travels in the form of wave as well as in the form of particle. Okay, particle. So light travels in the form of particle too. Particles. And these was proved by two methods. These are proved by two methods. Basically for your syllabus, this was proved by two methods. And in that one of the most important thing is photoelectric effect and black body radiation. By these two methods, scientists proved that light travels in the form of particle too, and we discussed deeply what is this by photoelectric effect and what is this by black body radiation. See, first we want to learn how to cook tea. After that, we learn many things. So we are just learning how to cook tea. Okay, now after that, you know particle means what? Particle means what? Particle means matter. See, for example, this is a pen. This is made up of small particle. All particles together form a matter. Similarly here, particles all together, particle forms your matter. And matter, we know anything which is made up of small particle, it is called as matter. And this matter, see, matter is basically particle nature. I just said this is made up of small particles, and this full is a matter which has mass and occupies some space, like matter. Now it is made up of small particles. Simple, which means matter is a particle. Very simple. Matter is a particle form, but matter forms wave nature also. How? See here, if light which is basically wave, if it can perform particle nature, then particle which is basically matter can perform wave nature. Yes, it is like you performing particle nature, then I will perform wave nature. Super, right? Super. So matter perform wave nature. And this was proved by, or you can say this was proved by using diffraction of electric beam, or this diffraction of electric beam was discovered by Davison and Germer experiment. Beautiful. Now basically what they did now, we know electron, a stream of electrons always travel in a straight line, but this electron started showing diffraction. Arey Baba, this diffraction, we only see diffraction in waves. But this electron is also showing diffraction. Why? It made a question. See, basically, electrons always travel in a straight line. Electron space, which is particle, it is atomic particle. Electron is a particle, which is atomic particle, and it's traveling in a straight line. But this electron, particles must travel in a straight line. But this electron started diffraction can only seen in waves, but why we are seeing same diffraction in light, in particle? Huge question mark. So that time this deviation and Germer's experiment help us to say that this particle can also form wave nature. Interesting, super interesting. And this is main discussed by one of the greatest scientists, de Broglie hypothesis. This is the main important. We'll discuss more about this. Okay, now basically this is a mindset. This is a clear-cut explanation why light behave both the nature and why matter behave both the nature. And this is the topic name. What is the topic? What is the lesson? Dual nature of light and matter. Light has two natures. Similarly, matter has two natures. Both have wave nature and particle nature. Simple case. And this is our in-depth knowledge. Okay, now let us see the first topic of your class, light as a particle. I just will discuss about photoelectric effect in this class. Last class itself we discussed photoelectric effect, but also in this class we'll discuss very depth photoelectric effect. See here, when a radiation of high energy, important, when a radiation of high energy and high frequency, high energy means high frequency and low wavelength. High frequency and low wavelength incident on the surface of metal, it start emitting electrons, or electrons are ejected outside. Simple thing. They are telling very simple thing. I will explain you the science behind this. See basically, where it is. No, work function now. Okay. See now simple thing. When a high energy fall on the metal, that high energy consists of high frequency but low wavelength. See, like this. Like this. High energy and low wavelength. See, wavelength is very less and your frequency is high. Wavelength is less, frequency is like this of wave, when fall on the metal, it start emitting electrons. See here electrons are coming outside. See here, electrons are coming outside. Okay, now super right. Now this energy, which energy is equals to, your h nu. Energy of light wave. We can say, like, I will write it here for your knowledge. Energy of light. E is equal to hf. And here h is your Planck's constant. Planck's constant, whose value is exactly, like not exactly, it's approximately. So until now, no one find the exact value of Planck's constant, and there is the constant don't have exact value. So 6.623 into 10 to the power of minus 34 Js, joules per second. Very simple. And your F is equals to frequency. And this frequency I can write it as C by lambda, which means frequency of sunlight or frequency of light is equal to C by lambda. So finally I can write as the energy of light is equals to H into C by lambda. C by lambda. Now, on this basis, they are asked many questions. On this basis, they are asked many questions. You must know what it is and why it is. Okay. And don't worry, I will give one small shortcut. We'll discuss small shortcut afterwards. For this, you remember this one. Okay. Now, fine. It's just simple. Photoelectric effect is very simple. When a energy, high energy radiation incident on the metal, it will emit some radiation. That's all. Photoelectric effect. Photoelectric. See, the name itself telling. Photo means what? Photo means photon. Photon means energy. Energy means what? Sunlight. This energy fall on the metal and it emits electrons. Photoelectric effect. Photoelectric effect. Now let us see some properties. Some properties of this photon. Properties of photon, or you can say particle nature of light. Particle nature of light. Particle nature of light. The particles of light is called as photon. See, I just said these particles travel now. See, from sunlight it's travel. This travel particle we call as photons. Photons, or you can say energy of packet, or you can say quanta of energy. See, both words, all the terms they can use, photon or energy of packet or quanta of energy. Both are equal. And this now, see, by using Newtonian mechanics, we can't define the mass of photon. See, there is a mass of photon, which we can't define by Newtonian mechanics. What is this Newtonian mechanics? The mechanics given by Newton. Your grandfather, Newton is there now. Newton gives you some mechanics. By using that mechanics, we can't define the mass of photon. Fix in your mind, by using Newtonian mechanics, we can't define the mass of photon. Now, one more thing. The mass of rest photon is 0. See, here. Rest means which is not moving. The mass of rest photon is 0, which means any proton which is at rest, its mass is 0. And basically in nature you can't find rest photon, because photon is always moving from this side. Photon is always moving. See, radiation, can you ever imagine sunlight at rest? No, you can't even imagine sunlight at rest. Similarly, it can't be rest, so photon never be 0. You can say photon never be 0, but if they ask, the rest photon have mass 0. And see here, the photon means what? Light. Photon means what? Light. Photon means energy. Energy means light. Simple test. Photon, energy is coming from sun, which is in the form of waves or particles that travel, that carrying from photon, it will hit to surface, which means photon only. And that photon travel with the speed of 29978924486 meter per second, which is almost equal to the 310 power of minus 8. One second. Now it's right. See, it is the speed of 3 into 10 to the power of 8 meter per second. This is the speed of light. Okay, now and photon travel irrespective of the frame of reference. See, I think this is a real thing. So in starting mechanics first 11th class, what? Forgot. Everything forgot. 11th class gone. Not remembering 11th class, everything forgot. Arey, what? Why? Okay, I will tell you. In vectors, motion in straight line. You was reading like frame of reference. There is some frame of reference. With the respect to frame of reference, we will measure all the motions, right? But this photon movement is not depend on your frame of reference. Photon movement is not depend on frame of reference. Photon travel irrespective to the frame of reference, which means very simple. When photon is traveling, if you travel opposite to photon, speed don't change. When photon is traveling opposite to you and you are traveling opposite to photon, that time also speed don't change. Now when you are traveling together with the photon, speed don't change. Speed remains constant. It is irrespective of frame of reference. Remember, this point is very important. Now let us see. You know I am going very quick. I think so I am going very quick. Am I going very quick? Wait one second. Wow. Hey, come on, man. Why? See this scratch. Okay. Now photon, you got some properties and you got photoelectric effect. Now let us show that definite mass and definite momentum of photon. This mass and this momentum of photon, let us define and complete this one. Let us define. See, we know that photon has energy E is equals to h nu, and this energy E is equals to h into c by lambda, and this is same for all. Now and we know h is equals to Planck's constant, which is equal to 6.636 into 10 to the power of minus 34 Js. We know this value. And in exams they will give you wavelength. See here, this is h is constant, c is constant. Now if they give this value, you can find this value. Easy thing. And if they give E value, you can find lambda value. Easy thing. Now for this also I will give one shortcut. Now let us take one more shortcut. We'll use shortcuts. E is equals to 1240 divided by lambda in nanometers is equals to, answer will be in EV. Answer will be in EV. Your answer will be in EV. See, this is shortcut. Use this. CBSC students, this is not for you. You must follow this full lengthy formula. This is formula for NEET and IIT aspirants. Okay, okay, remember, keep it here. Okay, this formula 1240 divided by wavelength in nanometer. See, if they are given wavelength like this Armstrong, you want to convert it into nanometer. Again, put this formula here. You will get exact answer in your EVs. Wait, I will rub this extracurricular activities. Okay. Now one thing. Energy we got. Now momentum is defined by P. Momentum is equals to C h by lambda. Momentum. This is your momentum, which is P is equal to h by lambda, or P is equals to E by C. See, very simple. In the place of h nu, see, take this one. Now can I write this as E by C is equals to h by mu, and take this, can I keep it here? I will get this value, right? This is your momentum, this is your energy value. Energy, and this is your momentum. Now remember this formula. This all important. This one, and shortcut, very important. Now let us see few things. Let us see what this steady fellow properties. Let us see some properties. Now these properties we discussed in the last class, and this class also we will discuss very deeply. See, photon of particular wavelength have same wavelength. Same wavelength. No. Rub this. Have have same energy, right? Same energy and same momentum. Very simple. See, very simple, very simple. Photon of particular wavelength. Let's say red. If you talk about red, if you take red light, it has some wavelength. Now if you take bright light, right? If you take low, not bright, dark, light bright, pink bright, say red bright, not bright, light bright, little bright. All this kind of they have same energy and same momentum. It is like you can think, if a light is very bright, maybe that energy is high, maybe momentum is high. No. If a light is very weak, very less light, you can think that energy is low, momentum is low. No, that is not the case. If you are taking a particular wavelength, if you are fixing a red light, then the energy and momentum is same. Energy and momentum, sir, it is not going to vary. I will explain. And see, next one, the collision of proton with a material particle is assumed to be perfectly elastic. See, this fellow, now this collision is there. Now can you see this collision? This collision, it is perfectly elastic. It is perfectly elastic collision. Very simple, that's all. The collision of particle is perfectly elastic collision. The collision of particle is perfectly elastic collision. Now see this last point. I will explain this last point. If the intensity of light is increased, then the number of photon is increased, but the wavelength and momentum not the wavelength and momentum. See, not the wavelength and momentum. They are telling this line justify this. Justify this. Very simple. When the intensity of light is increased, the number of photon increase, not the wavelength and momentum. See, very simple. I will tell you. Now imagine I am taking a light here. Now let's say power 80 watts, and one more light here with power 180 watts, and we know 100% we know that this has some radiation outside, and this is light. Let's say which color it will be good? Let's say which color? Red color. Okay, I will read here. Red color light. Okay, now super. Now this 80 watt bulb emits radiation, and it looks light. See, very light. And but this 180 watts look very bright. After seeing this, you can say that, sir, this is bright, this is not bright. Maybe wavelength is varying, maybe energy is varying. No, not the case. If it is the case, if it is increasing, if it is light, if it is bright, then the thing is number of photon is increasing. Number of photon is there now. Number of photon is increasing. Here see, number of photons is increasing, not the other thing. Now see here. In both difference, number of photons is increased. But if you take individual photon, it have same energy and same momentum. Intensity increase, it will have same energy. See, photon will have same energy and same momentum, but the number of photons coming outside in 1 second, it will increase. This is why some light appear very bright, some appear light bright. It is, see, when a light is appearing bright, Don't think that is energy is coming outside very high or momentum is changing. No, 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 no. The number of photons coming outside per second is very high. That's all. See, let us write here. What? The number of photon coming out is very high. Coming out very high. Coming out wait 1 second. Coming out coming out in 1 second is very high, very high. This is the reason why this appear bright, and here the number of photon coming out in second is less. This is the why. This is not bright, this is bright. This is case. This is why some appear very bright, some appear not bright, light. Okay, now energy and momentum of this photon is same, but the number of photons ejecting or eliminating, you can say it's high. Okay. Now let us see. No place up. Okay. Now photon over. Photon not over. Just the thing is this energy and momentum over. Now let us continue this and see wave function. What do you mean by wave function? In last class itself I said you wave function means it's a minimum energy required to eliminate one electron from surface of the metal. See, if we supply energy greater than the work function, even see, I'll tell you here. See here. Now this is your neutron. First circle, second, third. Okay. Now imagine you have electron here. And this is your valence shell, which means weakly bound. Now this electron can easily come out. But this nucleus, see, I will write here. This nucleus at low attractive force. This nucleus at low attractive force to this. Now normally the thing is the valence shell electrons wants to come out. They want to come out of the atom, but this small low attractive force is there now. It is not letting them to come outside. It is like come in. You are not supposed to go out. Come in. Like that it is escaping. So now if this electron must come out, then we must give some energy opposite to this attractive force. See, very simple. I will show you. Imagine this is your electron, this is your atom. Now this is your one single electron. Now this wants to come out. See, this wants to come out. This electron wants to come out, but this nucleus is not letting it to come out. See, don't go. Now if I apply some external energy equal to this attractive force, I can easily remove this. That external energy is called your wave function. Now remember, in an atom, valence electrons try to come outside, but nucleus adds a small attractive force on that. That's why it is not able to come outside. Now, if we want electron to come outside, we must apply some energy opposite to that attractive force. Okay, now the thing is, if you apply attractive force, then also there is a doubt. See here. Now, if the supply energy is greater than work function, minimum energy. Work function is what? Work function means minimum energy. I said now we are giving some energy opposite to this small attractive energy. That energy, work function, we call it as work function, and it is denoted by phi. Like this, okay, like this. Array, it becomes double. Now it's fine. Function. Now see this one. If we supply energy greater than wave function, even then there is no guarantee that electrons emission. Shit. See, for suppose now we are applying energy greater than or equal to your wave function. Now see, there is electrons in this, if we apply energy greater than wave function is minimum energy, we are applying, it is coming outside. Now this is minimum energy. Now if we apply energy more than your wave function, then also there is no guarantee that electrons can eliminate outside. Why? As electron loses energy while colliding the ions. Why? See here. Why? Very simple. No pressure. I will show you here. Now, for suppose this is your metal and it has electrons. Now, when you apply some external energy E value, maybe there is chances that this electron take this value and collide with other electrons, collide and lose all energy, See, it's the level of interesting it is. The level of interesting it is. Now, we saw that there is some energy we needed to remove outer electron. But that if we apply that energy, then also no guarantee that electron will come out. Sir, then what to do? How to do? Why to do? Where to do? When to do? Nothing to do. Just take your book, start reading. That's all. You will understand everything. Okay. Now. Okay. Again there is error. Now if we apply energy greater than our work function, then also no guarantee that electrons can come outside. Now see here. So when supply energy is greater than work function, electron may come out, may not come out. See, I said no guarantee, 50-50 chance. No guarantee, 50-50 chance. May or may not, no guarantee, 50-50. We are not telling that it won't come. We are not even telling it will come. 50-50. It may come, it may not come. It's up to its. So by this you can say three possibilities. By this you can say there are three possibilities. See here, three possibilities. What are those possibilities? There are three cases can be exist when we supply some energy. Very simple. Now supply energy is fully used fully for collision. First case, supply energy can be fully used for collision. See, very simple. Very interesting and very simple. Now this is your metal. This is your electrons. Now if suppose I am applying some energy here, if I am supplying some energy, let's say that energy is your let's say 10 volts, 10 eV energy. Now this electron using all the energy for collision. using all the energy for collision, using all the energy. Using all energy for collision, all energy, and no electrons is emitted, and no electron emitted. First case, supply energy is fully used by collision, fully used for collision. Okay, understood? Very easy, very easy. Now, second case, see, supply energy partial use. Partial means what? 50-50, or maybe partial using. Same again, electrons are here. Electrons are here, and these rays are falling here. And if we take 10 eV, some is going to collision. Let's say 4 eV for collision. Remaining electrons are eliminating outside, which is 6 eV. Balanced, partial. It may be different, 2, 3, 4, 5, whatever, different. Now the last case, and very important case, supply energy is fully used for emission. This is very, very important. Now, if it is your metal, now it has some electrons like this. Now, when the rays are falling on here, imagine with very simple 10 eV are falling, and no collision we are seeing, no collision, and this 10 volt used, and outside 10 electrons, or you can say 10 eV energy is released, fully used. Three cases, and this case is important. By this only Einstein find your father. Einstein find photoelectric effect. Okay, now let us see. Very simple case. There are 3 cases. See, I just said in the first work function for removing of outer electron, we must apply some extra energy which is opposite to some more attractive energy. Then also there is no guarantee that electrons can emit. Then also there is no guarantee that electrons can emit. Okay, now we can say that supply energy is greater than or work done. Then also no guarantee. Then there exist 3 cases that supply energy can fully be waste, partially, and fully used. Now, fully used is very important case for us. Now we will discuss that only. Now see here, electric supply energy greater than your work function. Last case. See, now this is very important. If electron making best use of incident energy, then it come out with a maximum kinetic energy. See, I said it now. Now if electron use full use, which means if I apply 10 electric volt, the outside electrons are coming with 10 electric volt, which means no collision. It is making its best use. At that time, this electrons come outside now. It has maximum kinetic energy. This is the last maximum kinetic energy. Above this kinetic energy don't exist in this photoelectric effect. That's it. Yes. Maximum kinetic energy. Very simple. Now, if electrons use the best of incident energy, then the electrons emitting outside, it's a maximum kinetic energy. Very simple. Now let us see some small very important derivations there. Not small. See, not derivation. I don't say it as derivation. See, maximum kinetic energy, right? maximum kinetic energy, which is equals to your supplied energy minus this wave function. Now how it comes, I will show you, don't worry, how it comes I will tell you, don't worry. Now your kinetic energy maximum is equals to E minus of F. Fine. Now see, if I apply 10 electric volt, no, once again. Now, if I apply one case, if I apply 10 electric volt and work done of any metal is 3 volt, then remaining is 6 volt. For suppose this metal has work done means what? The amount of energy required to come outside. Above that energy, it is not using a point energy also. It is just using, sorry, once again, sorry. See what I did in last time. Hey, it has some work energy, right? Oof. Okay, parallel, adjust. Now, see, a metal has some work function, which means the minimum energy required. Now, the energy we are making to fall, it is only minimum energy using. Remaining energy is coming outside. That's very simple. See, very simple. Now, any metal need minimum energy to eliminate electron outside. Now, when we apply some external energy, it will fall in, and this external energy is used only this minimum energy. Remaining all is coming outside. In other two cases, with external energy, extra energy is also using for collision. In this ideal case, only minimum energy is using, remaining energy is coming outside. Minimum energy is coming outside. That's all. See here itself. We applied 10 volts. Work function of this is this 4. Now remaining we got is 6. Very ideal case. Now remaining two cases, how it now? Remaining two cases, we applied 10 volt and work function is 3 volt plus 2 volt for collision. And we get here 4 volt. 6 plus 2, 8. What is this? Yeah. Hey, collision minus one. Wait. This comes minus here. Collision happening inside now. So, see here. Now we applied 10. 4 is its necessary energy work function. Extra 2 is eliminating due to collision. Remaining is 4. 2 we are losing extra. So this is not ideal case. This is not maximum value. This is not maximum kinetic energy. So maximum kinetic energy when electron use the best of incident radiation. When the electrons use the best of incident radiation. Okay now, fine now. If there is a confusion, please let me know. In next video we can clarify that confusion. Okay. Now see. Let us come to our small derivation. We know E max is equals to E value. We can write HF. Right. Now E max, energy max or kinetic energy max is equals to H into C lambda by this. Your final answer. Make a small change here. In this there is small work function, which is 4. Now eliminating is 6. Sorry guys, small. Now it has okay. Remaining is everything is fine. Only this one. It has some energy function, which means minimum energy required. Except that minimum energy, everything is coming outside. Okay. Now this is clear. This is important thing. Now let us say threshold frequency. Same. This is only little extended, threshold frequency. Threshold frequency. Now let us see what is this threshold frequency. It's a threshold means what you know. Threshold means in ancient times you heard threshold means it's like protection. Not that protection. In war and all we are using protection to protect us. Threshold, which means something which must cross that protection to kill us. Similarly here, some frequency must cross this threshold energy to perform photoelectric effect. Very simple. Frequency must cross this threshold frequency to perform photoelectric effect. See, I will tell you how. If you want, you can write the frequency. The frequency must be greater than threshold energy frequency to perform an photoelectric effect. Photoelectric effect. Now we know. We will calculate photoelectric effect formula. This we know. This we know exactly we know. And I can write it as like this. Yes, of course. Now frequency is equals to this dirty fellow. Okay. Now this value is your threshold frequency. This value is your threshold frequency. And finally, F must be greater than your threshold frequency, which means frequency of incident ray must be greater than frequency of threshold. Frequency of incident ray must be greater than threshold frequency. Do I need to write that? Okay. Frequency of incident ray or rays or radiation must be greater than threshold frequency. Threshold frequency. Clear up. Now this threshold frequency has a graph. That graph is for write it here, graph kinetic energy max versus frequency. Now remember this formula. This one is very important condition. Now about this condition we will see our graph how this comes. Very simple thing. Kinetic energy is equals to E minus U. This you know. Now kinetic energy max is equals to HF minus of H epsilon naught. See here, last page. Come to last page. See here. In last page we know epsilon naught is equals to wave function divided by H. Can I find from this epsilon naught work function? Yes, I can find work function like this. Yes, easy thing. Now take that, keep it here. Keep it here. One second. Okay. So simple. Now see this. Is it in the form of anything? Yes, it is in the form of y is equals to mx plus c. Y axis and h m slope, c intersection. C is equals to negative, which is intersection, and m is slope, which is positive, and y is your axis. Totally, this graph is telling that we are getting a graph which is intersecting at y-axis negative, but its slope is positive. Like this graph we want to draw. Very simple. See here your kinetic energy max one side here F. Very simple graph. See negative intersection at negative intersection. Okay, in y-axis negative intersection in y-axis, Now after that slope is positive. Slope is positive. See, simple. And this point is your epsilon naught, which means threshold frequency. The frequency, see here only see, frequency is greater than threshold frequency. At that time, emission is happening. Okay now, and this is your work function. And this area from this point to this point, threshold frequency, sorry, not threshold frequency. Okay, threshold frequency is higher. Threshold frequency is higher than your normal frequency. Threshold frequency is less than your what is it? In this condition, threshold frequency is less than your main frequency is less than your threshold frequency. Now in this case here, your frequency is greater than your threshold frequency. Super. And in exam we neglect this area. Because see, it is F means what? F means HF is equals to energy, and here F is negative, which means energy is negative. But can energy be negative? No. Negative energy. So we ignore this one. We take only upside line, which is positive. Okay now, fine now, super. Now let us see last thing. Threshold wavelength. Trisha wavelength. Very simple. Again thing. The wavelength. See, frequency must be high. In starting definition you studied high energy, which has high frequency, low wavelength. See, as frequency increase, wavelength decrease. Frequency increase, wavelength decrease. I will write here. Frequency increase, wavelength decrease. Okay now come to threshold frequency. The frequency below which the frequency of wavelength below which photoelectric take place. Very simple. The falling rays, the incident ray, that frequency, that wave's wavelength must be less than this metal wavelength or electron wavelength. Okay now, fine. Okay, now let us see how it's. E is this condition we know. Now can I write this as like this? Yeah, I can write. See, first h by f it will come. Again this case. Yeah, super. I am discussing only about wavelength. So can I write like this? Yes, I can write like this. Now if I want, see, I can write like this also. Yes, shifting gives me this. Okay, super thing. Now by this can I say as y max. See, this dirty fellow is your threshold wavelength. This is your threshold wavelength, and your wavelength, your real wavelength, your very real wavelength is less than your threshold wavelength. We got our condition, and we know this is equals to hc by value. And if we want wave function, we can derive wave function like this. Remember, very simple. Threshold wavelength, or you can say cutoff wavelength. Okay. Now same one thing. Again, graph is for versus. Sorry, I did wrong. Yeah, this is the wrong way of taking. Okay, one second. Kinetic energy max versus 1 by wavelength, which is very simple. In this energy max, in this axis 1 by wavelength. Same thing. We will take our one formula. Kinetic energy max is equals to E minus pi. Now we know kinetic energy max is equals to h nu minus of h nu naught. We know this one, and we will write here h nu, h is equals to c by lambda minus h is equals to c by lambda u, Now kinetic energy max, this is again, it is like y is equals to mx plus c. Again intersect is negative, slope m is positive, axis is y. Again same thing. It went very far. La 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 la. Hey guys, do you liking this? See, if someone is not understanding, let me know. See, this is the case, and after this it's increasing. Now in this place up to here your wavelength is is greater than your threshold wavelength. At this time it can't happen, negative, again same place. But in this area your wavelength is less than your threshold wavelength, and this we know wave function. Now we had one condition, I will write here, in this area. We know that frequency must be greater than or equal to threshold frequency for conduction, but wavelength must be less than the threshold wavelength. Then only we can see wavelength. We can see photoelectric effect. Now I think we got few our formulas, few our things. Now in next class we'll discuss all the problems about this. We'll end this class. I think it become very lengthy class. It's okay. In next class we'll define all the problems about this, and we'll end this class here itself. Thank you students. If you like this video, you know what to do. Just like, subscribe, and share this to your all the friends. If you want notes, if you want to communicate with me, or any doubt or any regarding any particular doubt, I can write in the paper and send you. You just need to join our join our WhatsApp channel, and in that also, if you want notes of these classes, you just need to join our Telegram group. I have provided both the links in the description. Okay, we'll meet in the next class. Until that, stay tuned to our channel, Added, the place where we add knowledge to your brain. We'll meet in the next class. Until that, tata, bye bye, see you.